Good afternoon. Welcome to Krishna's class. We are meeting for the first time in this new year. My best wishes to each and every one of you for a very happy new year. Let us continue with our explorations of topics in mathematics. Now what I want to take up is the following. You know that if you take L2 function on the interval minus pi to plus pi, then you can develop a Fourier series for that. And in the L2 norm, you have convergence of every Cauchy sequence in that. So it's a complete inner product space, or what you call a Hilbert space. Therefore, if you write down the Fourier series and take up the partial sums, they converge in the L2 now to the function you have started with. Okay, so you have the following: f belonging to L2t, and in L2t this is on the interval minus pi to pi. In fact, you can take a periodic function and then work on that. In L2t, if you use the norm as norm of 2 norm, this is equal to 1 by 2 pi integral to the power of half. Now this defines a norm, and it comes from the following inner product, namely one by 2 pi this is the inner product that you have, and this is a norm that comes out of this inner product. Now you have the Fourier series. The Fourier series is the following: f is, I don't put equal to, let me put it this way, equal to sigma minus infinity to plus infinity, infinity, Cn e to the power int. Okay. Now this is the Fourier series, where you have the Fourier coefficients, or the Cn's, are essentially given by and this is defined, this turns out to be 1 by 2 pi integral minus pi to pi so the coefficients are turn out to be f hat n is the transform of that, and using the trigonometric function e to the power int. This is what you have. Okay, now what you can show is the following, that is norm of f minus sigma k equal to minus n to plus n f hat k e to the power I k t under the 2 norm goes to 0 as n tends to infinity. Or in other words, the partial sum of the Fourier series converges to the function in the norm. Now the convergence, this is convergence in the okay. Now the question that you ask is the following, or what we want to investigate is the following. Suppose now you see that the continuous functions on t, which are essentially, let me write down what they are, then you would know exactly this is a subclass that you are talking about. Now we'll write the following. We will just recall the following. L2t is the f, which is complex value, Lebesgue measurable, Lebesgue measurable 2 pi functions on R. See, the geometry is essentially this. You look at the functions defined on T. Now let us look at T, the relation between the real line and T as follows. T is the unit circle. This is the unit circle in the complex plane. Let's see. This is mod z equal to 1. Now you take the real line. Take the real line. Imagine the real line is a string. Okay. Now you know that the circumference of the unit circle has length 2 pi. Okay. Therefore, what you do is you take this infinite string and start winding it around this particular circle. Okay. Then what happens? See, each 2 pi length bit of this would wind around once. And thus, because of you are considering the whole real line, it is going to be infinitely many. The the infinite string is appears to be wound around this particular unit circle infinitely many times. Okay, and what happens is, now you talk about continuous functions on this. What do you mean by continuous functions of that? The corresponding analog here is on R. You get what are called continuous functions which are periodic with period 2 pi, or the basic part of the function can be assumed to be defined on minus pi to pi. And let us write down what those functions are. So whatever pattern is here will get repeated. So you take the graph of the function defined here and then you see that because at minus pi and plus pi the function will take the same value. Okay, and then you repeat it. If you repeat it on every interval of length 2 pi, from pi to 3 pi, minus 3 pi to minus pi, etc., etc. You see the same pattern gets repeated. So that's what you mean by periodic, and this function has periodicity 2 pi. Okay, now you are taking Ct as the following. So what are the functions of Ct? Ct are continuous functions it's a function which is continuous, Lebesgue measurable, obviously. So Ct is periodic functions on R with period 2 pi. Now this is what you have, the Ct. Now you clearly to see that you have Ct is contained in L2. Now we are going to look at the function Ct. Okay, they are all now on the interval minus pi to plus pi. They are continuous functions. Okay, and if you take those functions on the whole of R, then it is going to be a continuous functions with period 2 pi. Therefore, whatever analysis you do on minus pi to plus pi will get repeated everywhere. So you get an idea of what the corresponding series you build up, whether it converges or not, etc., can be read from what happens on the interval minus pi to plus pi. So let us work on that now. Now our question is the following. Now one of the things that we observe is the following. Okay, so let me swipe it off. So Ct is a part of the inner product space. Okay, and one more thing that you can say is that CT is dense in L2. L2T, and CT is dense L2T. We are taking the the metric that is induced by the inner product. Okay, and now you have for F belonging to in fact you have L2T is contained in L1T. That's very easy to do. Okay, therefore for any F belonging to L1T, you see, you can write down the following. You can write down the series sigma minus infinity to plus infinity hat n e to the power n. These are the trigonometric functions e to the power n. N belonging to Z, and where f hat n is then given by 1 by 2 pi, where f hat n is equal to 1 by 2 pi integral minus pi to pi ft Now we are making use of the properties of the inner product, namely the following. Just to recall this, because you see that this f hat n is defined for all functions in L1. Because the problem is only about integrability of this, whether this integral exists or not, and f hat n is well defined for L1. Therefore, it is defined for L2T. Therefore, it is defined for all functions in C2T also. Okay. Now, it comes in the following way. Define now these functions and define, let FG be integral or 1 by 2 pi minus pi to plus pi now this is an inner product that comes. I mean, we are right now formally computing this. Okay, at least in L2 we can safely do all these exercises, and this makes sense. And then in that case, you see that you get F2 turns out to be 1 by 2 pi minus pi to 2 pi, as I wrote earlier, to the power half. This is the L2 now, and on L2T, now what further thing you have? You have, now you see these functions form an orthonormal set. This is what you have. You have equal to 1 by 2 pi e to the power I n t into e to the power minus I m, and that's equal to 1 whenever n equal to m and 0 n not equal. Now you see that this forms an orthonormal sequence defined on the interval minus pi to plus pi. Okay, and you can use the power of that and write for f belonging to L1, you can write Cn you can write f you write as an expansion, formal, this is formal, minus infinity to plus infinity Cn e to the power minus e to the power I n t, or this is equal to Cn un from our definition of un. This is a formal expansion, right? And use the orthonormality of these functions and compute Cn, and Cn turns out to be f hat n. It's a transform of that actually. Or I'll write this as inner product of f with so that's the usual expansion that you have. These are essentially the projection of f onto these vectors un. Okay, and then write this, and therefore you get this expression. So f becomes now, f is now, I'll put it this way, write it this way, and we can explore what exactly this means. Now what follows would be that now you form the partial sequence of this. You write let us write down the partial sequence. So consider sequence plus n which is equal to f hat k turns out to be now this is the partial sum of the previous. So you have functions of this kind phi n series. What happens? What is that you get then? When you see that these partial sums or this now what you have is this, that we have norm of this is what is called the, this is true for L2. This is the convergence result that you have. Okay, this is the L2 convergence. Now CT is a part of it. Now CT is now these are continuous functions now. CT functions are. So for everything this is true in particular infinity. Now in the norm psi n the sequence converges to f. Now the question that we want to take up is little more deeper. So the question that you ask is this. Which are continuous functions, obviously which are nice continuous functions. Does psi nt converge to ft for every t or on R? Because if you are taking the periodic functions, the functions belonging to that is for f belonging to Ct. This is what we are asking for f belonging to Ct. A very reasonable question, extremely reasonable question, because when you are considering L2T, there of course such statements do not make any sense, because the function itself is defined almost everywhere in the 11th question. And here, because you are working on continuous functions, it is a natural question to ask, does this partial sum or do these partial sums converge pointwise to the function or the value of the function at any t belonging to minus pi to plus pi? And since we are considering periodic functions on the interval minus on r, see that everywhere you are asking this question, is this going to converge pointwise, or at every point on the interval or on r, does the partial sums that you have, or do the partial sums converge to f pointwise for every t on this or on r for all f belonging to Ct. Now this is the question that you are going to investigate, and there are very fascinating surprises that you are going to get. Okay. Right? So we will investigate this and we will look at this problem in depth. So let us start working on this, and need some work to go through these ideas. Okay. Now let me write down the partial sums as follows. Let me introduce the right notation. So the question is this, let me write it formally. We take f belonging to Ct plus this is the question that you are asking. This is the one that you are investigating. And of course, it's clear that the Fourier series, so you are working on the partial sums, and that is the sequence that you are building. So this is equivalent to saying that we shall rename it converge to f x belonging to r this is the pointwise convergence that we are interested in. That is limit n tending to infinity of This is the question that you are asking. Okay. We know that psi n converges to F in the L2 now. And we also have the result, general result, that Ct is dense in L2 T. Okay. So all these results are available. So we will do some preliminary work today and then work out the proof, the details of the proof next time. Some formal computations that we do. This is what we do. Let that is, we take psi n to be what we have earlier designated as this. This is a bit more explicit in the sense that in our notation we have brought in that function f also into the picture, so that it is clear that what we are talking about is about a function f belonging to Ct, or f belonging to Ct. So then the first thing that we prove is that the nth partial sum of the Fourier series of f at the point given by equal to 1 upon 2 pi integral minus pi to pi ft dn. This we get as the kernel of the integral dt, where for n equal to etc. So denote this by 1. This is the partial sum. So this is what we want to prove first. I think this we have done earlier, probably somewhere in the context of the Fourier series when we were talking about Fourier series, but let us repeat. Now what you have is this. We are talking about periodic functions. Okay. Where equal to we'll use the dummy variable as t in this case. This is f hat n. Then what you have is this. We have Sn f x is then equal to sigma minus n2 plus n f hat k, that is the summation over k equal to hat k e to the power ik. Then formally is this really true? This is the question that we have posed. Okay, let's now compute this. So you have now we replace for this f hat k, and this is equal to f hat k we get as 1 by 2 pi integral minus pi to pi ft e to the power minus dt, that is f hat k e to the power I k. What we do is we take this inside and then work with this. So this is equal to 1 upon 2 pi integral minus pi to pi sigma minus n to n or I will put it this way, I will interchange the summation and integration. So I get here minus pi to pi. So it's a finite sum you are talking about. So for every n this works. Okay. 1 by 2 pi ft into sigma minus n to n e to the power I k x minus t So this turns out to be what is called the kernel of the integral. Okay. Now let Tn be defined by then what we have is this equal to integral minus pi to pi dt, where of course n e to the power ik x minus t. So this is the expression that we get. So the question that we ask is this. So we have got an expression, nice expression for Sn, the partial sum, in the form of an integral, and that is useful for estimating this integrals or this the convergence of this. So the question is infinity this is the question then. That is, we are asking for investigating pointwise convergence. Okay. Okay. Now, what turns out is that the investigations show that this does not happen. Okay. This is not true. So what we prove is that this question has we shall continue from here and then go ahead with the investigation. Therefore, what we have looked at is this, that for L2t, functions in L2t, the Fourier series converges in the L2 norm. You are asking the following question. Suppose you take the partial sums of the Fourier series. Okay. They form a sequence which converges to the given function in the L2 norm. Is the convergence still stronger than that? Suppose you restrict yourself to continuous functions on t, then can you assert that, very reasonable question, can you assert that they sequence, the partial sums do converge to pointwise to the given function? It's a very reasonable question that you ask. You are not asking for all the functions in L2, but you are asking for continuous functions. So the answer to this turns out to be in the negative. Now that is the surprise that you have. So there are lot of hidden, things concealed inside the Fourier series. Okay, even for a nice function like a continuous function, you cannot expect pointwise convergence in all situations. So thank you very much. Stop here.